it's kind of an odd day we came up here, and we got a lot of calls out there. You can still be doing this, and of course, the show must go on. It's Tim, who's always a great speaker. And of course, you know, the question on everybody's mind, the elephant in the sky, is the clouds, and are we going to be observing tonight? And probably not. I mean, if the clouds break, it might be a chance, but the domes will be open, the 60-inch will be open for, you know, you walk in there, there will be someone to show you the telescope itself and someone else down by the gears, so you get sort of an inside look there. And the 100-inch was actually just this last week re-illuminized. So it was taken apart. The illuminization was successful. The mirror is back upstairs, but they were scrambling, but there wasn't time to get reinstalled. But the tours, you know, you'll be able to go up in there and then actually see something much rarer in a way than looking through the telescope. You know, the telescope in pieces, in its different parts, and they'll tell you how it was, you know, the process for, it's an astounding piece of work that you have to do. I mean, that piece of glass that has to be removed is 4.5 tons. It's an amazing thing. And plus, if all goes well, the bottom is, you know, the mirror sits in the mirror cell, which is removed and set apart. You'll actually be able to get under the telescope and look up. They're going to open up the cover for it. It's something that no one is really, well, not no one, but maybe 100 people in the world. You know, it's like everyone's got a diamond ring and they spend so much for it, but this is an experience that 100 people in the world have experienced. You know, anyway, so it's, you know, it's you can boast. So now. So I got some notes here in what I was talking. Okay, the directions, the instructions. So as when you leave after the talk, you go out the door, you walk to your left. Many of you probably already know this. As you go, you will see where the garage is. That's where the food truck is. This time we're doing barbecue, which I had always been against because, you know, it's messy. But whatever, I was overruled, and they have a red light thing. So please clean your hands before you go into the telescope domes, and then we'll continue to have barbecue if it's stay clean. And then just beyond, you come to our sort of central intersection. That's where the restrooms are, one of those Hollywood restroom location trailers. We have to bring those up because we don't have bathrooms. This wasn't designed for, you know, a lot of people. One of our goals is to have bathrooms built where this one is set, and it takes a long time. I mean, we're on Forest Service land. It's Carnegie Institution owns the telescopes. We have to work through them, and it's just takes a lot of time. And I think we'll have some resolution in October. We'll be able to go forward with that process, but I'm not promising. Neither of them, they want us to do it, but they're not giving us any money yet. That's kind of what we're at the arm wrestle with them for. Then to the right, you'll see the 16-inch telescope. You probably know, and then across the bridge to your left, you'll see the bridge that takes you to the 100-inch telescope. So go and enjoy both of those. Now, I know that most of you came here wanting to look through the telescopes, and it's not going to happen, most likely. Clouds may break, I mean, miracles could happen, but this is astronomy, you know, God decides, and, you know, you learn, it's a lesson, you know, you don't always get what you want. But that's one thing I've noticed is astronomers live a long time, so they learn that lesson really young, and I think that has something to do with it. Patience, equanimity, acceptance. So anyway, that's my philosophy. All right, there we go. I think I got that part covered. Oh no, what I was going to say is, for those who want, now we're really grateful that you paid this money to come. I mean, Tim is worth the $50 alone. But I know you came here for the telescopes as well. So those who want, you email, you know, we'll give you a 50% discount to come to another opportunity, another one of the lectures this season, not next season, okay? It's got to be this season. email lectures at mtwilson, Mount Wilson, with mt.edu, and we'll accommodate you. But if you just want to give us the money anyway and not take advantage or buy a full price ticket, we'll accept that as well,
because we need the money.
We need the money. We love money, but we love this place. And we need the money to keep, you know, I don't know if some of you have been, if you've been coming here since we started this in 1918. I hope you're seeing it. 2018.
Are you recording this?
But anyway, I hope you're seeing the incremental improvements we've been able to do over the years. And, you know, these events really contribute to that, and we thank you for that. So anyway, with that, I'm going to introduce Tim, and I think I've said enough. One thing I did, I came across a quote from Hubble, which I thought was kind of interesting. It says, so we do not know why we were born into this world, but we can try to find out what the sort of world it is. And that's what happened here in the first half of the last century, and that's what Tim's going to talk about, the revolutionary changes in our view of the universe. So anyway, with that, Tim, you can describe yourself.
Oh, boy. Do you need to turn on my lapel mic?
Oh, you're on.
I'm on, okay. He says the microphone's already on. That means you can hear me, right? Now you better be able to hear me. I'm supposed to talk about myself. First, let me get this thing out of my face, begging your pardon. Most of you probably already know something about me. Okay, I have a master's degree in physics, so I'm really good at making stuff up. You'll never know. It will be great. I've been at Mount Wilson Observatory for 43 years. I've been up and down that road you drove up so many times. But no, I would not try to drive up that road blindfold. Only a crazy person would do that, and I might be insane, but I'm not crazy. So, my reason for being here is to talk about Mount Wilson Observatory and the dawn of modern cosmology. And to start with, you might ask, why Mount Wilson Observatory? There are a lot of other observatories around. Why this one? What's so special about this place that it's the one we talk about when we talk about the dawn of modern cosmology? Well, first off, the guy in the corner here, George Ellery Hale, was in some small way, like most of us, in the corner of his mind, maniacal in his devotion to figuring out what's going on in the universe. His personal interest was in studying the sun. He had his own observatory in Kenwood, a suburb of Chicago, where he studied the sun and earned an international reputation. And he took over Yerkes Observatory at the University of Chicago. But he was always limited by the capabilities of the observatories he had, the amount of money that was available to him, either through his family or the institutions. So when he was finally on his own, he got away from Yerkes, came here in 1904, and Mount Wilson Observatory, his brainchild, really just kind of exploded into the world of astronomy. This picture shows you 5 telescopes, each one of which was the biggest in the world when it was built. There are 3 solar telescopes, the horizontal SNO solar telescope, the 60-foot tower, and the 150-foot tower. I show the dates when they were finished here, 1904, 1908, 1912. They were the largest solar telescopes in the world from 1904 to 1962. The 60-inch telescope was built simultaneous with the 60-foot tower, was the largest in the world from 1908 until 1917, when it was eclipsed by the 100-inch telescope, which was the largest in the world from 1917 until 1949. 5 telescopes, all of them the largest in the world when they were built. Nothing like that ever happened before, and nothing like that has happened since. There's only one other observatory I know of that's got more than one telescope on its campus. It was the largest in the world, and that's the Keck Observatories in Mauna Kea, because they built two 10-meter telescopes at once, and that's the only competition. And all 5 of these telescopes were built over a 13-year period. You can't build one big telescope in 13 years now, and the buying power of the money that was spent to build these 5 telescopes would probably not be enough to build that one telescope now. So this is kind of a miracle. When we say that Mount Wilson Observatory dominated the world of astronomy throughout the first half of the 20th century, that's not an exaggeration. It really did. These were the biggest telescopes for half a century. This is where you came when you wanted to do real cutting-edge astronomy. And I'm going to talk about cosmology and the major role that Mount Wilson Observatory had in creating this rather fascinating science. But we want to say a little bit about cosmology before Mount Wilson, because we have to admit that before Mount Wilson, there actually was astronomy. There were people doing astronomy. There were good astronomers. It didn't all just start here. And you might ask, what is cosmology anyway? So I'm going to give you a one-slide lecture on cosmology, because I don't have time to go through the whole science. So this is it. This is cosmology boiled down to its real essence. The only difference between these two, you know, the guy hauling the club, the caveman, he looks up and where all that stuff came from. And the modern fancy astronomer with his big telescope and fancy education like mine looks up at the stars and says, I wonder where all that stuff came from. It's the only difference between these two is that the modern scientist has a much more nuanced and sophisticated level of ignorance than the guy with the club. Otherwise, neither one of them knows how to answer the question. They don't know where it came from, but they don't even know for sure how to answer the question. They're in the same boat. And the caveman on the left, I call him a caveman. How do I know if he was in a cave? But I'm going to show you. The caveman on the left is no exaggeration, because I'm going to compare a panorama from the Hall of Bulls, or the Salle des Taureaux, in the Lascaux cave paintings in France. The cave painting on the upper right here, 17,000 years old. And I'm comparing it to a page out of John Flamsteed's Atlas Celeste, the 1776 edition. The legend, the myth of Taurus the bull, the Greek legend, obviously has roots that go way beyond the Greek legend. You can see it's a bull 17,000 years ago. These paintings are so old, they predate Conan the Barbarian. So you know this is really old stuff. Somebody was looking at the sky. Somebody was paying attention. There's a painting, the Taurus, where it says Aldebaran. That's the Hyades open cluster. You can see the Pleiades. You can see Orion's belt. For many, 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 many thousands of years, people have been looking up at the sky, wondering where all that stuff came from, and occasionally, just occasionally, maybe wondering, what is that? But mostly, where did it all come from? Now, I can't spend the rest of the hour talking about old cosmology, or you'll never hear about Mount Wilson Observatory. So I'm going to offer a suggestion, a reading list of 2 books, both by Edward Harrison, who is an amazingly good writer, a seriously talented real cosmologist. Masks of the Universe is a book in which Harrison goes through the mystical, magical, theological, religious, philosophical origins of cosmological thought way back before anybody knew anything. It's all prose, it's well written, and you don't need to be a scientist to understand it. You need to be able to read, and most of you look like you can do that. The book on the right, Edward Harrison is also a sophisticated, real-life cosmologist, and that's probably the best book on cosmology you'll ever find for people who are not cosmologists and scientists. If you know some math and physics, it's in the book. That'll treat you well. If you don't, there's plenty of prose, lots of interesting questions and problems to think about. So if you really want to learn about cosmology and what it really is, and you don't already know, and if you think you know, you probably don't, read his book on cosmology. This is my reading list. This is my suggestion. And yes, this talk is being recorded. It will be on YouTube. So if you forget the books, eventually when our people get it on the channel, you'll be able to pull it up and you say, oh, those are the books he was talking about. I'm going to start my scientific discussion with the invention of the telescope, which was really maybe the biggest moment in the history of astronomy other than the invention of the eye by nature during the process of evolution. All of a sudden, people could see things they had never seen before and could never see before. It's the first step in releasing us from what I call the tyranny of the eye. First you magnify, and then you go into multi-wavelength astronomy. You start to do infrared and radio and X-ray, things you can't see. But the telescope is the first really big moment. Now the guy who gets credit for inventing the telescope is Hans Lippershey, who's pictured here in the upper left. He's an eyeglass maker, and the reason he gets credit is because he got to the patent office before Jacob Matthias did. Matthias was furious and in response smashed every piece of equipment he ever built into rubble, burned every single piece of paper he had, ran away and was never heard of again because he was furious that Lippershey was ahead of him. Lippershey did go to the patent office, but they didn't give him a patent because they said this idea was already floating around and it's not bright enough, and so no. So maybe Matthias should have hung around. However, I would like to point out the kids in the doorway in the upper left. Lippershey gets credit for inventing the telescope. He's an eyeglass maker. He didn't have a lot of time to play around. He's making eyeglasses. So I'll bet even money what the real inventors of the telescope are the two kids in the doorway. And they're out there playing around. They run in and say, hey, Dad, look what we can do. And then they run out and go, and Dad's go, yeah, look what they can do, and becomes the inventor of the telescope. So it's probably them who invented it, not him. But he's the one who gets the credit for it. Meanwhile, this guy, Galileo, is the one who gets credit for being the first person to use a telescope to do astronomy. That's not really true. He wasn't the first person to do astronomy with a telescope, but he was the first person to do it systematically, consistently, to carefully study everything he was look beyond the surface, had a nuanced and complicated view of what he was looking at. So he was the first person to do real scientific astronomy with a telescope. He told the Italian Navy that he invented the telescope so he'd get royalties for selling them to the Italian Navy, because if you can see who's coming from a long way, that's an advantage if you're in the Navy. This guy, Thomas Harriot, is the one who actually looked through a telescope to do astronomy first, as far as we can tell in the historical record. His drawings predate those of Galileo by several months, his drawings and his notebook entries. But he did it, and he kind of looked and said, okay, I see bright things, dark things, the moon looks interesting, I see sunspots, the stars look interesting, okay, I'm done. And he went off and did something else. So the legacy of the telescope is Galileo's, not Harriot. But if you really want to be picky about your history, Harriot came first, and you can win a lot of bets at the bar on who really looked through a telescope first to do astronomy. The next big thing is figuring out how far away stuff is. Because even though you can see the rings of Saturn, the moons of Jupiter, the phases of Venus, sunspots, double stars in a telescope, you don't know how far away any of that is. And the real root of astrophysics and cosmology is how far away is it? So the very first stellar parallax measurements were made by Friedrich Wilhelm Bessel, who's much better known as a mathematician than an astronomer. He looked at 61 Cygni, measured its parallax angle. He got a distance of 10.3 light years, and modern values about 11.4. And there's no uncertainties attached to those. They're little slightly squishy numbers, pretty much the same. So he did a good job. He got the right distance. The mechanism of parallax is described in the diagram over on the left. Most of you are probably aware of the fact that you have two eyes. Most of you can probably see through both of your eyes most of the time. Just imagine that the Earth in January is one eye and the Earth in July is the other eye. And the distance between your eyes is the diameter of the Earth's orbit. And then if you've never done it before, hold your finger up in front of your face and look at it with your right eye, and then your left eye, and your right eye, and your left eye, and watch your finger bounce back and forth. Nobody's doing it because you're all too embarrassed, but go ahead, it works, And you'll see your finger bounce back and forth, right? Well, that's trigonometric parallax. And if you know the distance between your eyes, and you measure the angular shift of your finger, you can figure out how far away your finger is from your face. And so the stars in the background are too far away, they don't shift, but the star in the foreground shift, as indicated in the two little diagrams, and voila. Now you know how to figure out how far away stuff is. So if we fast forward to the dawn of the 20th century, around the year 1900, which is the last year of the 19th century, not the first year of the 20th century. We have a nice long calendar argument about that. But about that time, people knew the distance through trigonometric parallax to about 60 stars, certainly less than 100. I played around with papers published at that time, and the number I got was 60. Could have been more, but I don't believe more than 100. And that's just a few stars very nearby. And you can see the limit in distance for this method that Bessel used, only about 350 light years, plus or minus a few. So I only see things nearby, 60 to 100 stars just right around us. And that's all they knew. Everything beyond that was guesswork. So later on, other methods were invented at Mount Wilson, spectroscopic parallax, for instance, which give you a little bit farther, take you out a couple of thousand light years. But there's all nearby distances. You need a way to find out distances that are way far away if you want to do cosmology. So the next big breakthrough comes when Henrietta Leavitt, who was a computer at Harvard College Observatory, realized in 1908 that something was going on with the variable stars in the small Magellanic Cloud. She probably actually knew in 1908 that there was a period luminosity relationship, but she needed more data, more analysis to prove it, to show that it really worked, and she published that in 1912. And the two plots that are shown here, I'm going to blow them up and talk a little bit more about them in a minute. Usually in these discussions you'll hear about Henrietta's discovery and on they go. But she did not know how far away the stars were. You cannot use the information from Henrietta alone to get a distance because you don't know how to calibrate it. That was done by Einar Hertzsprung in 1913. He used statistical methods to calibrate her data to a real distance scale so you can figure out how far away these things really are. And I want to look at this a little more carefully because this is the root of all the discoveries made here early on. This is a really critical thing because it allows you to get distances over millions of light years, not just 100. So it's really important. So if you look at the plot on the left, the vertical axis is the apparent magnitude of the star on the astronomical magnitude scale that some of you are probably familiar with. If you're not familiar with it, bright is up and dim is down. And that's really all you need to know. The higher up you go, the brighter you get. The number on the horizontal axis is the period in days of variability of the star. And by that I mean the star gets bright and dim and bright and dim and bright and dim and bright and dim. Now that you're all hypnotized, now the distance between the two bright peaks is the period of variability for the star. But you notice the best statistical fit to that data is a curve. And curves are difficult things to work with. You have to actually use more complicated equations. It's a lot easier to work with a line. So the plot on the right replaces the period with the base 10 logarithm of the period. If you remember your high school algebra, you know what that is. If you don't remember your high school algebra, you know, there are community colleges, there are books, you know, you can fix this problem, you know, just... If you don't know what a logarithm is and you're not going to go try to remember your high school algebra, all you need to know is that if you do that, you get a straight line. And straight lines, as you might guess, are easier to deal with than funny-looking curves. So Henrietta got a straight line. And if you remember your high school algebra, the little equation in the lower right, you'll recognize as the slope-intercept form of the equation for a straight line, the simplest thing in the world you can do. The big capital M is the absolute magnitude of the star, which means its true intrinsic brightness. Its apparent brightness, you know, because you're looking at it and say it looks that bright. Now you calculate the true brightness. The difference between them gives you distance. So what we're doing, the data are kind of noisy. They're a little sloppy. As you can see, the points are bouncing around. There's a line drawn through them. How do you know that's the right line? Maybe just get a ruler and draw a line is not good enough. There are statistical ways to figure it out. The A in the little lowercase a in the equation is the slope of the line. That means it's which direction is the line pointing. If you diddle that number, you will twist the line like this. So you can twist a line by diddling that number. The letter C in the end of the equation tells you where that line intercepts the vertical axis. So if you diddle that number, you lift the line up and down like this. So now you can do this, you can diddle the numbers around and do all these things. And the B inside the square brackets, which you don't normally need, allows you to move the line horizontally. So what you do is you do this a zillion times, and you find the line that through various statistical rules is the best fit to the data. Nowadays you can do that in an instant on your cell phone and not worry about it. But in Henrietta's day, it required clunky old mechanical calculators, lots of pencils, lots of paper, and lots of time, and that's how she did it. She didn't have a cell phone, didn't have an electronic computer, took a lot of work. But with the calibration from Hertzsprung, she was able to use this equation to get real distances. That is an important thing to remember because that brings us to the beginnings of the cosmological discoveries at Mount Wilson Observatory, and it brings us to this guy, Harlow Shapley, who is now using the 60-inch telescope. Now I'll remind you, if you didn't already know, Mount Wilson Observatory was founded as Mount Wilson Solar Observatory by George L. Hale. He built the solar telescopes first. His interest was in looking at the sun, but he knew you needed to study other stars, so he built the 60-inch telescope and the 100-inch telescope. They didn't build them with anything specific in mind. They didn't know, let's see, we are going to discover cosmology. How do we do that? Let's build a telescope and do it. Not quite. He just built the telescope and got a bunch of smart people and said, go use this telescope and discover smart things. And they did. And Harlow Shapley is one of those people. Now Harlow, here's the 60-inch telescope, which under happier circumstances you would look through tonight, but that's probably not going to happen. It looks a lot different now than it did then, but there it is. Now remember, Henrietta published her discovery in 1912, Hertzsprung calibrated it in 1914, and Harlow came to Mount Wilson in 1914. It hot off the presses and began to work, and he was primarily observing globular clusters surrounding the Milky Way. What is a globular cluster, you might ask? Interlude for pretty modern picture. This is a globular cluster. This is Messier object number 13. Yeah, maybe 25,000 light years away. It's kind of hard to get the distance. 145 light years across. Who knows how many stars? Every time I try to start counting, my phone goes off and I lose count. Somewhere between 300,000 and 500,000. Nobody really knows. There are a whole lot of these, maybe 150 floating around the Milky Way that form a halo around the galaxy, which was called the sidereal universe at the time. And, of course, photobomb, there's a distant galaxy, NGC 6207, 30 million light years away. It's more than 1,000 times farther away than the cluster. When you look at a picture like this, remember you're seeing something that has depth in it. Some of that stuff can be way far away in the background, and some of it can be right up close. It's a flat picture, and if you don't pay attention, you'll never know. So Harlow used this to look at the Milky Way, which he called the sidereal universe, and he mapped out the globular clusters. Now he said a lot about the Milky Way. He talked about the dark lanes that we now know are dust. He called them a zone of avoidance where star clusters can't form and are ripped apart by strange forces, gravity, or electromagnetism, you don't know what. But aside from laying out a distance scale and schematic diagram for the Milky Way, he did something else of real philosophical interest and importance, which is illustrated by this diagram. And remember, they didn't have graphics departments back in those like they do now for modern magazines and journals, where you can make really fancy diagrams. This is pretty much the best they could do back then. What did he discover? You are here. That's where Harlow was, and the center is here. That's where the center of the distribution of globular clusters was, which we assume is the center of the sidereal universe, and indeed it is the center of the Milky Way galaxy in the direction of Sagittarius. And you'll notice they are not in the same place. Ever since that cave guy in the earlier slide with the club was thinking about the universe and assumed probably that he was at the center of it, people have been arguing over, are we at the center of the universe or not? And throughout those many thousands of years, it has always been guesswork. Nobody actually knew. You could argue one way or another, but nobody ever actually knew through some specific, definitive measurement that we are not at the center of the universe until Harlow Shapley came along and from 1914 to 1919 proved it for the first time in human history. And we kind of overlook that, but it's a philosophically interesting point. And just to make the story complete, this is what we think the Milky Way looks like now. Obviously, we cannot get out of it and turn around and take a picture of it because it's so big, and you have to go a long way and spend a long time to get there. So we know a lot more about the Milky Way than he did, and indeed, as the blue circle shows you, you are here and that yellow bar is at the center of the Milky Way galaxy. And it's a good thing we're here and not there, because the real estate near the center of the galaxy is a lot less favorable to human life. And so being out here is a good thing. It's a big thing. How many stars does it have? I put 140 billion here because that's sort of the average of all the funny numbers everybody comes up with, from 500 billion to practically 1 or something. So yeah, 140 billion. Maybe it's a couple of 100,000 light years across. Harlow Shapley overestimated the size and overestimated the distance scales in the Milky Way. He thought it was about 300,000 light years across. Standard answer you will get now is 100,000 light years. Probably the best number is 200,000 light years. So anyway, this is what the Milky Way galaxy looks like now. And we actually have a pretty good handle on that. The Milky Way galaxy is something we know really well now, starting with Harlow. The rest of the universe, okay, there are some open questions about that. So the next chapter in our adventure is Edwin Hubble, who comes to Mount Wilson Observatory in 1919. Now remember, that's just when Harlow was finishing up with his 60-inch and his work on the galaxy. Hubble comes, and we put him to work in the 60-inch, And we still do that today. If you want to become a telescope operator here at Mount Wilson Observatory, that can be arranged. We have instructors, we have a process for doing that, but we will not let you simply walk into the 100-inch dome and start pushing buttons. You go into the 60-inch and we train you and you get used to it and you operate it and you move it around and you play with it and you work it for a while. Then when you're comfortable with the 60-inch, we'll let you go learn how to use the 100-inch. And they treated Hubble exactly the same way. He went into the 60-inch and the night assistant took care of it and he got used to the 60-inch. Then he went to the 100-inch. There's the 100-inch telescope. Around 1940, largest telescope in the world from 1917 to 1949. And remembering that it's the largest telescope in the world is going to come in handy. Hubble was looking at things called spiral nebula. So, you asked me what a globular cluster is. You didn't, but I assumed you did. You're not asking me what a spiral nebula is, but you want to. You just won't. So, I'll tell you anyway. So there are these fuzzy things. Nebula is a Latin word for fuzzy, foggy, smoky, whatever. Something like that. And so the fuzzy things in the sky are all nebula, one way or another. And so the third Lord Rosse used his Leviathan of Parsonstown, the 72-inch specular reflector, which is diagrammed here on the lower left. It was a real kludge of a telescope sitting in a meridian transit mount. You stare to the south and wait for the sky to move whatever it is you want to look at in front of your telescope, because you can't move the telescope to look at it except a little bit, maybe 1 hour on either side of the meridian. And in those days, they didn't have cameras. They made drawings. And they would look through the telescope and stare as the seeing fuzzes things out and it gets clear. And then when you're convinced that that little feature you see is real, you get out your little pencil and you go, okay, I've done that. And then you stare for longer. And then there's this other feature. And then once you're convinced that's real, and you build the drawing. There's still people who do that. And you build the drawing piece by piece, slowly. And there's an 1845 drawing over on the left, and next to it is a modern photograph scaled and rotated. And as you can see, Lord Rosse's drawing does a pretty good job. He really did see a lot of features. He saw the spiral arms. He was the one who invented the term spiral nebula. He was the one who first came up with this idea of spiral nebula. He was convinced that he could see stars in it and that it was what we would call an island universe, a separate system way outside our own galaxy. There was no scientific reason, but he just believed it. There's no way he saw individual stars in that galaxy. That did not happen. At the same time, the well-known philosopher Immanuel Kant had come up with the same idea, the island universe idea, and the Swedish religious philosopher named Swedenborg also came up with the idea, and I have no idea why Swedenborg was involved in this, because he was a completely religious philosopher who had his own branch of Christianity. Why he even worried about galaxies, I don't know, but he was in there. Maybe he didn't like Kant or something, but anyway, this is where spiral nebula come from. And then from then on, the big debate was, what are they and how far away are they? Are they nearby clouds of dust and gas, or are they distant clusters of stars? People argued and people had reasons for believing both. Well, Hubble did not make drawings. He made photographs on glass plates with photographic emulsion. And you see him here, the picture on the left. He is at the Newtonian platform of the 100-inch telescope. The big piece in front of him, the Newtonian top cage of the telescope, is in the 100-inch dome now. It came back maybe a year ago from the Smithsonian Institution. They had it for a long time. When they decided they didn't want to display it for a while anymore, we said, it belongs to us this way, if you don't mind. And they shipped it back. And it's on, if you go and if you tour into the 100-inch tonight, you should be able to see it with a mannequin of Hubble standing next to it, I think. So Hubble in this picture is looking through a tiny eyepiece that has crosshairs in it, and there's a star where the crosshairs cross. And the problem is you need to make sure your photographic plate is true in its pointing at what you want to see as the telescope moves through a long exposure, in this case 45 minutes. Exposures could be hours long. You don't want the image to smear. You don't want to get a double image. So you stare through the eyepiece and make sure that star stays right at the point where the crosshairs cross. You'll see Hubble has one hand up here and another hand down here on two wheels. Those two wheels adjust the position of the glass plate. Eventually they were able to diddle the drive on the telescope, but in these days they couldn't. So it would adjust the position of the glass plate. So the imperfections in the drive system of the telescope would not smear the image because he would keep the image in place. But you see what this means. You have to sit there and not move. You have to keep staring through that little eyepiece and constantly make sure everything is lined up. And if a sudden urge to leave the telescope comes upon you, you must close the photographic shutter, take care of whatever got you away from the telescope, come back, make sure you're aligned exactly on the same star again, and then open the photographic shutter. But you have to stay there. And if it's winter and it's 20 degrees and the air is blowing down the back of your neck and you're freezing, tough luck. You're an astronomer. That's what you do for a living. You just stay there and do it. At the end of World War II, the U.S. Army Air Forces surplused a very large number of electrically heated flying suits for high-altitude bombers, and they were all snapped up with amazing speed by astronomers all over the world. My brother was an astronomer at Lowell Observatory, and he used one. You could plug yourself in. It was a lot better than the way things had been done before. But there you are. Hubble is not making a drawing like Lord Rosse. He's making pictures. And one of the many pictures he made is this one. Plate H335H. One of those H's is Hubble, and the other one is either Hooker or 100-inch. They both start with an H. Looks great. This plate is a 45-minute exposure. The original is a 4x5 glass plate, little thing like this. You can blow it up in great big. It's amazing how much resolution it has. What he's looking for are novae, and they're marked with an N on this plot. One of the arguments was novae are kind of rare. They don't happen very often. They're little stellar explosions, stuff falling from a regular star onto a white dwarf star, and some stuff goes boom on the surface of the white dwarf star. They can happen over and over again, but they're not periodic. They don't happen very often. There's a long time between them. They're rare. Hubble's looking at this galaxy. This is Messier object number 31, the Great Spiral Nebula in Andromeda. He's looking at it and he sees 3 nova. Well, he already knows there's something going on because nova are very rare. Why would there be 3 of them in this little patch of sky? And they're dim. And he knows they're bright. But they're dim. They look dim, so it's got to be far away. He already thinks that this is a distant stellar system just by looking at the nova. But then he realizes this nova up on the upper right there, it went away and came back, and went away and came back, and went away and came back, and went away and came back. And now you're all hypnotized again. That means it's a variable star, not a nova. He knew it was a Cepheid-class variable star from the roughly 30-day periodicity. So he knew if he found more of them, he could figure out a number. How far away is this thing for real? And be the first person ever to find the distance to a spiral nebula. So he went to work and did exactly that. He also knew that Cepheid-class variable stars like novae are very bright. But this is the biggest telescope in the world. It's 100 inches in aperture, and you can barely see it on this image, which means it's got to be far away. So he had plenty of evidence where he could just say, they're far away. How far away are they? Let's go get lunch. Okay. But he wants to know how far away they are. And he did. He figured it out. And on November 23rd, 1924, for the very first time, the public discovered what he was up to. Now, there are other astronomers knew this already. His colleagues, people he's working with here, people at other observatories, but it was kind of a secret until it was published in the New York Times. You will notice that Hubble's name is not spelled the way I have spelled it. It is consistently misspelled throughout this article, or is it? We had a Hubble family reunion here maybe 8 years ago, something like that. I was their tour guide. They came up and took a special tour. And there were at least a half a dozen different spellings of the name Hubble in that group. There was one L, one B, two B's, one L, one B, two L's, the L over here, the E over there. There were several different spellings, and this is one of them. So this is a valid spelling in the Hubble family tree. It's just not the way Edwin spelled it. Why did they spell it this way in the New York Times? I don't know. But I do want to draw your attention to this paragraph, which you probably can't read, but I will. The results are striking in their confirmation of the view that these spiral nebula are distant stellar systems. They are found to be about 10 times as far away as the small Magellanic Cloud, or at a distance of the order of 1 million light years. This means that light traveling at the rate of 186,000 miles a second has required 1 million years to reach us from these nebula, and that we are observing them by light which left them in the Pliocene age upon the Earth. This is something that we kind of think about now routinely. It seems ordinary to us. Yes, it's that far away. Yes, it took the light to get there. But these words in this paragraph are the very first time in print in human history that I know of that this kind of thought entered the human consciousness. And suddenly we are aware that the universe is so big that it takes light traveling its fantastic speed to take a really long time to get here. So this paragraph represents a major change in the way people in general think about the universe. It's just not a scientific thing. It's not something that's boring. It's the way people who are not astronomers, even people who have never heard of Hubble, there are actually 2 or 3 people in the world who have never heard of Hubble, have heard that the universe is that big and things are that far away. So it's a really big deal. Now, Edwin went on to publish NGC 6822 in 1925, M33 in 1926, and M31, the big one, Messier object number 31 in 1929. The 2 distances I have here, the first one is the one that Hubble reported in his paper, and the second one is what we now know to be the distance. Shapley overestimated the size of the Milky Way. Hubble underestimated the size of the universe. It's because there were problems with the methodologies, there were problems with the data. There were things that neither one of them knew that we know now that we'll talk about in a few minutes that fix these problems. But this is not the end of the story. There's a part 2 to Hubble's story. He has now proven to us that the universe is so big, light can take millions, maybe billions of years to get to us from so far away. But he also discovered that the universe was doing something. And now we need to set a little context, because this German guy that you may or may not have heard of somewhere along the line came up with an idea called relativity, which actually predates him by hundreds of years, but he came up with a different version of it, one which he called special relativity, because it deals with the special case of things moving around in straight lines at constant speeds, and then general relativity, which deals with accelerated motion. And while he was doing all this, he kind of stumbled by necessity over a new theory of gravitation, the structure of space-time, curvature of space-time, all this good stuff. All modern cosmology and physics, theoretically at least, is based on an understanding of Einstein's theories. But Einstein's theory requires the universe to be doing something. It's either collapsing or it's expanding, but it can't sit still. It's got to do something. So he asked all the astronomers, what's the universe doing? They all said nothing. Okay, so in 1917 he diddled his theory so the universe would do nothing. And then Edwin Hubble comes along and says, the universe is expanding. And then Einstein's like, oh, what did I do that for? I had a chance, I could have argued the universe must be expanding, but he didn't. So what's going on? In 1917, Albert diddled his equations so he could make the universe do nothing. But remember, by 1925 to 1929, Hubble had demonstrated that the universe was made up of very distant galaxies. In 1922, Alexander Friedman solved Einstein's equations in a consistent way to build a nice, consistent cosmological model without the diddle factor, the cosmological constant, that Einstein had introduced. So, hey, this looks good. And then in 1927, a Belgian Catholic priest named Georges Lemaitre discovered that he could build a model using Friedman's equations of an expanding universe. And he was very happy with this discovery, and he published it in French in the Annals of the Scientific Society of Brussels, which means nobody read it. And they simply didn't know that he had done this. Now, remember that, because it's going to become interesting in a few minutes. Simultaneous with his publishing of the distance to M31, in the same month, March 1929, Hubble published another paper in the Proceedings of the National Academy of Sciences of the United States of America, looking at the distances to various galaxies that he had determined and plotting them against velocities derived from spectroscopic redshifts that had been figured out by Vesto Slipher at Lowell Observatory. And he first presented what's now called the redshift distance relationship. What's really interesting about this paper, perhaps, is that he forgot to tell anybody that he was using Vesto Slipher's data, which is actually not very polite and will get you into trouble these days, and got you into trouble in those days too. And so yes, there was a problem with that, but he got around that later on. Now, you didn't ask me what a spiral nebula was, but I told you anyway. And you're not asking me what a redshift is, but suppose you did. Okay, well, what's a redshift? Well, these colored things here, these rainbow colored things over here on your right, are spectra. And so the rainbow of light in the background comes out from the thing you're looking at, and the dark places are where specific wavelengths or specific colors have been absorbed as they're on their way towards you. So we call this a spectrum, especially when it's got those dark lines in it. The one on the bottom is a laboratory spectrum, and then there are galaxies nearby, distant and very distant, and you'll notice as the arrows show you, spectral features shift towards the red end of the spectrum the farther away you get. And that can be interpreted as a Doppler velocity, Doppler shift velocity from simple physics. The diagram over on the left illustrates this from Milton Hummerson's paper in the Astrophysical Journal in 1931. It's really hard to see, as I've put here, and it's hard to see in the version that you get off the web. You got to have the real thing in a really good version of the diagram to see it. But suffice to say, it does show you how the H and K lines of calcium shift towards the red as you get farther away. So, Hubble and Hummerson got together, and in 1931 published another paper, this time using Hummerson's redshift values, and they put this redshift distance relationship all the way out to over 100 million light years. And you'll notice I made a comment here on the plot on the left, if you hadn't noticed it before. The slope of the line is something called the Hubble constant, which we will want to know about. Now, Hubble had been the first to publish an observed redshift distance relationship. Now remember, Georges Lemaitre published his paper in 1927 in French and nobody read it because of the funny journal it was printed in. So later on, while the famous scientist Sir Arthur Eddington was giving a talk to a bunch of people saying, this is really weird, we've no idea how to interpret this, what's all this redshift distance relationship, what do we do with this, how do we do with this? There was a guy named Georges Lemaitre in his audience and he went, excuse me, I did that already. You what? I figured it out, I figured it, published it like back in 1927. And nobody read it. So an English translation of that paper was published in 1931, same year as Hubble and Humason, in the monthly notices of the Royal Astronomical Society. In the French version of the paper, there is a prediction of a redshift distance relationship, which does not appear in the English language version of the paper, which has fostered a long-standing cottage industry of conspiracy theory that Edwin Hubble bought off the mystery translator to take that out of Lemaitre's paper so Hubble would get full credit for discovering the expansion of the universe and not Lemaitre. And so for years this has been a mystery and people have been writing letters in the journals, who translated this paper, was it really, would Hubble really do that? And people say, yeah, Hubble was that kind of guy, and other people say, no, Hubble wasn't that kind of guy. A few years ago, an enterprising historian rummaging through the dusty archives of the monthly notices of the Royal Astronomical Society discovered a letter written by Georges Lemaitre to the editor of monthly notices, revealing that he himself was the mystery translator who translated his own paper from French to English. And he took it out on purpose because he said, my theory doesn't matter anymore because since then Hubble has done it for real. He's figured it out, he's measured it. Who needs to know what I did? So I just took it out. It wastes space. So another perfectly good conspiracy theory, shot to heck. But so meanwhile, remember that Hubble underestimated the size of the universe and Shapley overestimated the size of the galaxy. Well, there were some problems. One of the problems is solved by Walter Baade, a Mount Wilson Observatory astronomer. He used the 100-inch telescope and the 200-inch telescope at Palomar to prove there's more than one kind of Cepheid variable. You need two distance luminosity relationships, or redshift luminosity relationship, not one. And so he split the period luminosity relationship, is what I meant to say, even if it's not what I said. The period luminosity relationship, he split it into two, instantly solved the problem, doubled the age of the universe, doubled the size of the universe, which is really very good because at the time it appeared that the universe was younger than a large number of stars in it, which does not bode well for your theory of cosmology. So you need to fix that, and Baade fixed that. And as soon as Baade had got done in 1956, along came Alan Sandage in 1958, and he said, well, I think Hubble mistook some compact H2 regions for stars in very distant galaxies where they're very small, and there were some other problems picking the brightest star in a galaxy or galaxy cluster. And so he fixed some other mistakes, and he came up with a value for Hubble's constant of 75 kilometers per second per megaparsec with a possible error factor of 2, which means it's a really sloppy number, but still 75 is an interesting number. So here is a plot that shows you the calculated values for Hubble's constant as a period, a function of time, different people doing different studies. Way back in the old days, like Hubble himself and other people who followed him, they came up with values between 400 and 600, which means the universe is no more than 1 or 2 billion years old, which was a real problem for geologists who would just beat the astronomers over the head and say, no, the Earth is not that young, you fools, and say, well, I'm sorry, but the universe. But you notice the two red lines, the one on the left is Baade publishing his correction in 1956, Sandage publishing his correction in 1958, and finally, values for the Hubble constant go down under 100 and settle in around this 70-ish region. The Hubble constant is just a constant of proportionality between the velocity and the distance. So you if you invert it, you just take 1 over the Hubble constant, you get the age of the universe. And so it's a very simple thing. Once you have a value for Hubble's constant, which tells you how fast the universe is expanding, you get the age. And so I've made a table here for you. So when we get down to the 70-ish region, you've got a universe that's 12, 13, 14 billion years old, which is good. That's what the cosmic microwave background people say these days. Yeah, about 14 billion. Yeah, it works good. The earlier numbers are not working out so well. So the Hubble Space Telescope, strangely enough named after Edwin Hubble, look at the same variable star Edwin Hubble first looked at in 1923. And there's an image of it from the Hubble Space Telescope, very same star. And the Space Telescope had what's called a key project, and their job was to discover the value of this Hubble constant to within plus or minus 10%. And down here at the bottom of the abstract of the paper, they published their final results in 2001. You'll notice the Hubble Key Project came up with 72 plus or minus 8 kilometers per second per megaparsec, which looks very much like Alan Sandage's approximately 75, so from 1958. And so not much happening from 1958 to 2001. Looks pretty good. We've got Hubble's constant nailed down. So at this point, this is where I'm going to leave the scientific discussion for a moment. We have laid out the basic framework of expanding universe, Big Bang cosmology, but you notice at the bottom of this abstract there are a bunch of different ways to come up with Hubble's constant. And these different ways of doing it create problems. Now, we already solved the old problems by making Hubble's constant a nice, comfortable number, and everybody's happy, but these annoying astronomers keep studying it, and they create new problems, and suddenly things aren't so comfortable anymore, and things are difficult to understand. But I'm not the one who's going to tell you that. In July, John Mulcahy is going to tell you that. So now that you've been to my talk, look at the schedule. Come in July. John Mulcahy is now the director of Carnegie Observatory. This is the very first Carnegie Observatory, I will remind you, is going to sort of pick up where I left off and talk about Hubble's universe and cosmology today. But before I go, I want to introduce you to an interesting idea. And in a moment, I'm going to ask for a volunteer from the audience, so get your courage up. It turns out, by odd coincidence, the number of inches in a mile is very nearly the same as the number of astronomical units in a light year. Astronomical unit is the average distance between the Earth and the Sun. Close enough for government work. So if you pick a scale to create a scale model of the universe, and you pick that scale to be 1 inch for astronomical unit, your approximation is good to about 0.1%, which is really amazing for any kind of approximation. That's really good. And so to illustrate what this means, what I need is a 4-foot-tall volunteer from the audience. And I think there's 1 or 2 people out there who are, do I have a 4-foot volunteer? Hey, I have a 4-foot volunteer. Come down here. Oh boy, what's your name?
Simon.
Simon?
Yeah.
Okay, Simon. Come, stand up here so people can see you. Can you stand up there? Okay. Simon is 4 feet tall. Now, why did I ask for a 4-foot volunteer? Well, 4 feet's 48 inches. And Pluto never gets farther from the sun than 48 astronomical units. So if I put the sun at the tip of Simon's brilliant head, Pluto is going to be down here where his feet are, and Jupiter is going to be right around the word playful. So this lays out what we normally call the solar system. But that's wrong. That's not the solar system. That's just the inner solar system, the realm of the planets. So Simon is my realm of the planets ruler, where all our spacecraft and satellites are buzzing around. But the gravitational influence of the sun goes out about 1.5 light years, which means we have to go 1.5 miles over Simon's Head to find the edge of the solar system. You didn't know the solar system was that big, did you? You have to go up 1.5 miles. If we want to find the Voyager 1 spacecraft right now, it's going to be right about the top of the screen. That's where the Voyager 1 spacecraft is. It's going to take it 30,000 years to get to that 1.5 mile mark. So when people tell you Voyager has left the solar system, not yet. It's going to take a while. Where's the nearest star? 4.25 light years away. We have to go 4.25 miles over Simon's Head. That's a long way, isn't it? We have to go 4.25 miles of nothing to get to the nearest star. And that galaxy that Edwin looked at, M31, is 2.5 million light years away. The moon never gets farther than 250,000 miles from the Earth, which means on your scale model we have to go 2.5 million miles over Simon's Head, which is 10 times farther than the farthest the moon ever gets on your scale model. Hopefully this impresses upon you the fact that the universe is very big and mostly very empty. There's just not much there. And of course, the galaxies that go beyond that go billions and billions of miles. If you want to know where the edge of the solar system is, universe, pardon me, you have to go all the way out to where the Voyager 1 spacecraft is now for real in order to find the edge of your scale model. So there you are. The universe is a big place, isn't it? Thank you, Simon. And so with that, I'm done. Thank you.